Okay, hello everyone. Today we will learn about discrete random variables and their probability distributions for. Okay. Okay, let's solve the example 3.17 of the hypergeometric probability distribution. An industrial product is shipped in lots of 20. Testing to determine whether an item is defective is costly, and hence the manufacturer samples his production rather than using 100 inspection plan. So because the finding defective is costly, manufacturer use sampling approach. Manufacturer samples some amount of lots rather than 100% inspection. A sampling plan constructed to minimize the number of defectives shipped to customers calls for sampling 5 items from each lot and rejecting the lot if more than one defective is observed. Okay, so it's the manufacturer sampling 5 items and rejecting the lot if more than one defective is observed. Okay, and if a lot contains 4 defectives, okay, so we have 20 lots, and among them 4 are defectives. What is the probability that it will be rejected? And we are sampling 5, and if our sample is more than one defectives, so if we have defective of 2, 3, 4, then we reject it. So we are calculating probability of this random variable y, the number of defectives get 2, 3, or 4. So here this is for first problem, and the second problem is what is the expected number of defectives in the sample of 5, and the third problem is what is the variance of the number of defectives in the sample of 5. Okay, so here the random variable of our interest is the number of defectives, and which follows hypergeometric distribution. Um, so, the random variable y is the number of defectives in the sample of 5, and y follows hypergeometric distribution with we have 20 samples and we have 4 defectives among them, and we are sampling 5. And what would be the probability that it will be rejected? So the probability of reject is actually probability of y equals 2 um, plus probability of y equals 3 and probability of y equals 4. And actually this is 1 minus probability of y equals 0 and minus probability of y equals 1. And which one do you prefer? You can solve it the way you'd like, but probably this is a little bit easier because you can calculate 2 of hypergeometric probabilities here. So it would be 1 minus we are choosing 20 choose 5, and you choose among 4 defectives you choose 0, and among 16 normal you choose 5, which is y equals 1, and for y equals 1 20 choose 5, among 4 defectives you choose 1, and among 16 normal you choose 4. Okay, so this is the probability. You can calculate it with your calculator. And for the expected value of y and the variance of y, you can use the formula that you learned in the previous chapter, this chapter, the hypergeometric prob the previous lecture last week. The EY would be n formula for EY is NR over N, and this is 20, and we are sampling 5, and there's full defectives, which is 1. And for the variance, yeah, refer the formula, and then you can calculate this one as well. Okay. Homework for chapter 3.7 is follows. Uh, the chapter 3.8 is about the Poisson distribution, and this Poisson distribution is used for modeling the number of events in the time interval. So it's about probability of a given number of events occurring in a fixed interval of time or space. If these events occur with a known constant mean rate and independently of the time since the last event. Okay, so the example of the Poisson distribution would be the uh, the number of typos in the textbook, or something like the number of deaths from the disease, or something like that. Uh, okay, and uh, we we say if the y random variable y follows Poisson distribution, we describe it as y follow Poisson with parameter lambda, which is mean rate. And a random variable y is said to have a Poisson probability distribution if and only if this. The probability of y is this one. Okay. To understand the Poisson distribution, let's think about the relationship with binomial distribution. The situation for Poisson distribution is number of event happened inside of the time interval. So let's say this is the time interval, and the Poisson distribution is the number of events inside of this interval. And actually, if we divide this interval as large number of tiny subintervals, let's say n number of intervals, and probably we can divide this interval small enough so that only one event happen inside of the small subintervals. Then then we could describe a binomial distribution um, to these subintervals. All these subintervals are independent, and let's say the probability of event happen inside of this subinterval as p. So let's describe situation this way. Consider time period as being split up into n subintervals, and only one accident happen in a subinterval is p. Since we divide this subinterval very small enough, the probability of more than one accident in subinterval is 0. So we can describe this situation as binomial distribution. So actually this is result as n goes to infinity, binomial distribution NP converges to Poisson lambda, where lambda equals NP. This is what we want to derive here, and and the situation here can be described as binomial distribution. So binomial n choose y number of events happen, and choose y, and p2 probability for the event success, and there's y times of event, and also 1 minus p times n minus y. This is the binomial distribution, and if we uh, goes to infinity, like infinite times of subintervals. If we divide this interval like this, and what would be the limiting distribution of this? And here and choose y. Okay, limit and choose y is n times n minus 1 n minus y plus 1. There is y number of these, and here and factorial y factorial. Okay, and also p from here, p equals lambda over n, so lambda over n to y, and 1 minus lambda over n to n minus y. Okay, and from here, this limit is about the n. So let's take out the variable not depend on y, which is y factorial. Y factorial can go out, and also lambda to y's can go out. Lambda to y's can go out, and limit n goes to infinity, and here we have n minus 1 dot 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 n minus y plus 1, and we have y number of n's, n to y's, and actually the number of these are n y, and so we can write this n to y's as n dot 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 n for the future use, and times 1 minus lambda over n to minus y, and times 1 minus n lambda over n to n. And here, this term is like as n over n is 1 times n minus 1 over n. This becomes 1 minus 1 over n dot dot dot, and this one becomes 1 minus n y minus 1 over n. And as n goes to infinity, this term converges to 1. This term converges to 1 because this term, the 1 over n converges to 0, and y minus 1, and here the y is very small value relative to n, because y is fixed value, and when y is fixed, n goes to infinity, so this the y minus 1 over n converges to 0, so this term also goes to 1, and thus, since the same reason, as n goes to infinity, this term also goes to 0, and this one goes to 1. And what about this term? So let's look at this term. Limit n goes to infinity, 1 minus lambda over n to n. And actually, this is e2 minus lambda from the calculus. If you learned calculus class or 통계수학, statistical mathematics class, that will be covered from that. Because of this, the whole thing here becomes y factorial lambda y and e to the minus lambda. So as a result, we can see that the binomial distribution converges to Poisson distribution, and we can think of this situation like this. Poisson distribution is the number of events happen inside of this time interval, and if we and actually in the assumption of Poisson distribution, the time time points are independent, so we can divide this time event as independent subintervals. And if we divide this as like n number of subintervals, we can think of the number of event happen inside of this interval as the binomial distribution with np, and the as we as n goes to infinity, the situation here can be described as the Poisson distribution. So this is the relationship between Poisson and binomial distribution. Okay, let's go on to example 3.18. Show that the probabilities assigned by the Poisson probability distribution satisfy the requirement that Py is greater than or equal to 0 and less than or equal to 1 for all y, and the sum of y, sum of probability of y equals to 1. And before we go on this problem, I think we should mention this first. You should know the Taylor series. And actually, in statistics, there's Taylor series comes many times. So you should learn this formula. You learn this from calculus class or 통계수학 class. Okay, so and let's look at this. Let's say fx is e to x, and what's the Taylor expansion at a equals 0? What would be at a equals 0? What would be Taylor expansion of e to x? And fx is e to x, and f prime x is again e to x, f second prime x is again e to x. And at a equals 0, f0 is 1. And what about the next term? Next term is 1 factorial. Here f prime, this is again 1. And here x minus 0, so this is x. Okay, the second term is again 1 over 2 factorial x second, plus the third term is 1 over 3 factorial x third, and plus dot dot dot. Okay, this is Taylor expansion of e to x, and so this e to x can be said like uh, x equals I equals 0 to infinity x factorial I factorial. Okay, I factorial x to I. This can be described this way. Okay, and let's uh, look at our probability of y of this, and we want to show this. Firstly, to show this one, the probability of y is greater than or equal to 0 and less than or equal to 1. Okay, here because of lambda is always greater than 0, each term is greater than 0. So we can see that probability of y is greater than 0 all the time. And also mm, also let's prove this thing first, then each of py should be less than 1. So let's show this. The first we show that every probability is greater than 0, and then let's look at this. Y equals 0 to infinity y factorial lambda to y and e to the minus lambda. And here this e2 minus lambda do not depend on y, so we take this outside of the summation, y equals 0 to infinity, and y factorial lambda 2 y. And what would be this thing? Compare it with this, and you can know that this is e2 lambda. Here I said I equals 0 to infinity I factorial xi. If you change this I to y, then this is exactly this thing, and this one is 1. So we showed that this one is 1, and so each p of y is greater than 0, so each p of y is less than 1. So this is the solution of this example 3.18. Okay, let's look at the next example. Example 3.19. Suppose that a random system of police patrol is devised so that a patrol officer may visit a given bit location y uh, uh, may visit a given bit location y times per half-hour period, with each location being visited an average of once per time period. Okay, assume that y possesses approximately a Poisson probability distribution. Calculate the probability. So the y, the okay, here y follows the Poisson distribution with mean rate average of once per period 1. Okay, and calculate the probability that the patrol officer will miss a given location during a half-hour period. Probability that patrol officer will miss, which is y equals 0, the probability of y equals 0. And what is the probability that it will be visited once? Visited once, probability of y equals 1, and twice, probability of y equals 2, and at least once, probability of y is greater than or equal to 1, and this would be 1 minus probability of y equals 0. Okay, so we know the distribution related to y, and also what we should derive. So pro y follows Poisson distribution with mean rate 1, and this is the Poisson distribution. So we can calculate each probability of y equals 0, and this is 0 factorial, and actually 0 factorial is 1, as you know, and lambda is 1. 1 to 0 is 1, and e to the minus 1. So this is the e to the minus 1, and probability of y equals 1. Probability of y equals 1 is 1 factorial. E to 0. E to 1 minus 1. Oh, that's right. Oh, sorry. E2 minus 1. This is correct. And lambda 1 to 1. Oh, this is again E2 minus 1. Probability of y is 2. It is 2 factorial. 2 factorial. Lambda is 1. And E2 minus 1. Okay. And what would be the probability of y is greater than or equal to 1? This is 1 minus e2 minus 1. Okay, then by using calculator you can know this number, so you can calculate each probability. Okay, let's move on to example 3.20. A certain type of tree has seedlings randomly dispersed in a large area, with the mean density of seedling being approximately 5 per square yard. if a forester randomly locates 10 one-square yard sampling regions in the area, find the probability that none of the regions will contain seedlings. Okay, so the forester randomly locate 10 square yard sampling regions. Uh, there's 5 per square yard. So for 10 square yard, there would be 50 in the region. So it would follow Poisson 50 and probability that none of the region will contain seedling would be P0. This is lambda is 50, 50 to zeros, e to the minus 50. This one is 1, so the probability is e to the minus 50. And also there's the other way around. The you can set random variable of y as here. If you read this line, then probably you would write y follows Poisson distribution of y, and you calculated the probability that none of the region will contain seedling for the scale yard. So if you set up this, like if you set up Poisson 5, um, as just as like the textbook solved, then probably you calculate probability of y equals 0 with e to the minus 5, and the problem is you want to find the probability that none of the regions will contain seedlings. So for a given square yard, um, the probability of the region do not contain seedling is this thing, and actually you have 10 number of regions. This is the probability for 1 square yard, and since you have 10 sampling regions, you have 10 10 number of these, so which is e to the minus 5 to 10, and which is e to the minus 50. So using this approach or the other approach, everything have the same conclusion. So you can solve this way or that way as you like. Okay, let's move on to theorem 3.11. This is about the expected value and variance of y when y follows Poisson distribution. So if y is a random variable possessing a Poisson distribution with parameter lambda, then the expected value of y follows y is lambda, and the variance of y is again lambda. Okay, let's look at this. So the probability distribution for y is this, and the e of y is from the definition, y is 0 to infinity y times y factorial lambda to y and e to the minus lambda. And actually this one, if y equals 0, the first term is 0, so you can start from y equals 1 to infinity, and uh, also you can cancel this y and y factorial, so this is y minus 1 factorial, and to match this as y minus 1, you can go 1 lambda out, and since lambda is not dependent on y, you can take out lambda here, and so you have y minus 1 number of lambdas and e to the minus lambda, and from here you have you can use similar trick. let y minus 1 as z, then this summation becomes z from 0 to infinity, and this one becomes z factorial lambda to z and e to minus lambda. And since this one is again Poisson distribution, so the sum of this is 1. So this one becomes lambda. Okay, this is proof for the expected value. And for the variance of y, actually by using the similar trick, like y minus 1 uh, trick plus, yeah, this kind of trick, you can derive the this one similar way. So you can do this by yourself for the exercise. Okay. Okay, here are homework problem sets for chapter 3.8. From chapter 3.9, I'm going to describe moment and moment generating functions. And from here, it considers a set of numerical descriptive measures that uniquely determine Py. And actually, this is very important. The moment generating function uniquely determine their distribution. So there's one-to-one correspondence between the distribution and their moment generating function. You will learn the usefulness of this thing from the example. Okay, let's define moment and moment generating function. Um, from definition 3.12, the case moment of a random variable y taken about the origin is defined to be e to the yk. So this is said to be case moment and is denoted by mu k dash. And the case moment of a random variable y taken about its mean, its case central moment of y is denoted by this one, expected value of y minus mu to case, and is denoted by mu k. Okay, and here comes the moment generating function. The moment generating function mt for a random variable y is defined to be mt equals e to the ty. Okay, and we say that a moment generating function for y exists if there exists a positive constant b such that mt is finite for this one. Yeah, okay, this is definition for moment generating function, and um, let's move on. Okay, from let's look at the moment generating function more precisely. So the moment generating function, by using Taylor expansion, the e to the ty can be described this way. We already saw the Taylor expansion of e to x in the Poisson slide. So with the same calculation, e to ty can be described as this. And by using this, the moment generating function can be described this way. So here is e to expected value of e to ty, and this, by definition of expectation, here this is function of y. The expected value of function of y is that function e to ty py, this by definition, and then this can be written as this. This e to ty becomes this, and this thing can be rewritten as this, and then this one is 1, and from here this one is expected value of y, which is the first moment, and that is mu1 dash. And from here, from the second term, this one is the expected value of y square, which is second moment, which is mu2 dash. And from the third term, this is our third moment, and which is mu3 dash. Okay. Okay, next one is Theorem 3.12. If moment generating function mt exists, then for any positive integer k, uh, this. And what it means is that from the moment generating function, you can derive the moment by differentiating to get the kth moment. You get the derivative k times and put t equals 0 for your moment, then you will get the moment. In other words, if you find the kth derivative of mt with respect to t and then set t equals 0, the result will be the kth moment, which is expected value of y to k. Okay, and actually it can you can check from this formula, and this is mt. This is our mt, and let's think about our k is 1. So dt dmt, what's this? It is mu1t, mu1 dash, and if you get the derivative, which is plus 2t and 2 cancelled, so t mu2 dash plus 3t square, and 3 cancels, so it is t square 2 factorial of mu3 dash plus dot dot dot. And so if you put t equals 0 from here, then you will get mu1 dash. And what about when k equals 2? dt square mt. You get the derivative one more time from here. The constant derivative of constant is 0, and the derivative of the second term is mu2 dash, and the derivative of the third term, it becomes t mu3 dash plus for the first term it would be t square 2 factorial mu first plus dot dot dot. And if you put from here, if you put t equals 0, then it will be mu2 dash, which is the second moment. So by this way, you can derive the kth moment from the moment generating function. Okay.
Thank you.